Welcome back to G Fun Facts Online. Today we are exploring a shift so fundamental, it is literally reshaping the landscape of technology. We are talking about the end of the flat Earth. No, not the conspiracy theory. We are talking about the physical reality of the computer chip. For over 5 decades, the semiconductor industry has marched to the beat of Moore's law. The relentless shrinking of transistors, from micrometers to nanometers, and now to angstroms, has been the engine of the digital revolution. We have essentially flattened the world of electronics, printing billions of tiny switches onto two-dimensional silicon wafers, expanding outward like a sprawling suburban metropolis. But today, that sprawl has hit a wall. We are running out of space, we are running out of power, and we are running out of money. The flat Earth era of computing is ending. As we push the boundaries of physics with 2 nanometers and 1.4 nanometers process nodes, the cost of lithography, which is the process of printing the circuits, is skyrocketing. The wires connecting these tiny transistors are becoming so thin that they act more like resistors, choking the speed of the very chips they are meant to enable. Worse still is the memory wall, which is the widening gap between how fast a processor can think and how fast it can fetch data. In a 2D world, memory sits next to logic, connected by long, power-hungry wires. It is like having a supercomputer in New York that has to fetch every byte of data from a library in Los Angeles. This brings us to the topic of today: monolithic 3D integrated circuits, or M3D-ICs. If traditional chips are suburban sprawl, monolithic 3D-ICs are the skyscrapers of the future. Instead of spreading transistors out, we are stacking them up. This isn't the stacking you might know from high bandwidth memory or chiplets, where finished chips are glued together. This is true sequential integration, building a second, third, or fourth floor of a skyscraper directly on top of the first, atom by atom, connection by connection. This technology promises to rewire the fundamental DNA of computing, offering interconnects 10,000 times denser than today's best packaging technologies. It promises to slash power consumption by 50% while boosting performance by 40% without shrinking a single transistor. To understand the magnitude of monolithic 3D, we must first distinguish it from its predecessors. The term 3D-IC has been around for years, but it usually refers to TSV-based 3D stacking, also known as parallel integration. In current 3D technology, like HBM memory stacks or AMD's 3D V-cache, manufacturers create 2 separate chips or dies in 2 different factories or at different times. They then polish them until they are paper thin and stack them on top of each other. To connect them, they drill relatively large holes called through-silicon vias, or TSVs. The limit here is that TSVs are huge in silicon terms, micrometers wide. They are like elevator shafts that take up valuable floor space. You can only fit a few thousand of them on a chip before they start eating up too much area. This limits you to block-level integration, putting a whole block of memory on top of a whole block of logic. The new way, monolithic 3D, is radically different. You do not glue 2 finished chips together. You build the first layer of transistors, tier 1, on a silicon wafer, just like normal. Then, instead of finishing the chip, you deposit a fresh, ultra-thin layer of silicon, or another material, directly on top of the first layer. You then process this new layer to create a second tier of transistors. Because you are using the same lithography machines to print the top layer as the bottom layer, the alignment is perfect. You do not need big elevator shafts. Instead, you use monolithic inter-tier vias, or MIVs. These are tiny nanometers wide, roughly the size of regular metal wires. This means you can have 100 million vertical connections per square millimeter. The implication is staggering. You aren't limited to stacking blocks. You can stack logic gates. You can split a single logic gate, like a NAND gate, in half, putting the PMOS transistors on the top floor and the NMOS transistors on the bottom floor. This is transistor-level granularity, and it changes everything. If monolithic 3D is so revolutionary, why don't we have it yet? The answer is heat. Making high-performance transistors for the bottom layer requires extreme heat, over 1000 degrees Celsius, to activate the dopants and crystallize the silicon. You build the bottom layer at 1000 degrees, and it is robust. Then you add copper wires to connect the bottom layer. Copper melts at 1085 degrees, but more importantly, it starts migrating and destroying transistors at anything above 400 degrees. If you then try to build the top layer using the standard 1000-degree process, you will melt the copper wires and destroy the transistors in the bottom layer. This is the thermal budget challenge. The top floor must be built at temperatures below 400 to 500 degrees, or the foundation will collapse. Research institutes like CEA-Leti in France have pioneered a process called CoolCube to solve this. It involves a suite of cool manufacturing tricks. First is SmartCut. Instead of growing silicon on top, which is hot and slow, they take a separate donor wafer of high-quality crystalline silicon, peel off an ultra-thin slice using hydrogen implantation to create a cleavage plane, and bond it to the bottom wafer at room temperature. Second is laser annealing. To activate the transistors on the top layer, they need heat. Instead of baking the whole wafer in an oven, they use nanosecond ultraviolet lasers. These lasers pulse so fast that they melt the top surface of the silicon to activate it, but the heat dissipates before it has time to travel down to the bottom layer. It is like searing a tuna steak, cooked on the outside, raw and safe on the inside. Third is solid-phase epitaxy. This allows silicon to recrystallize at much lower temperatures, around 500 to 600 degrees, over a longer time, which is just low enough to be safe for some robust bottom-tier interconnects, like tungsten, if carefully managed. While silicon is the king of the bottom tier, the thermal constraints of the top tier have forced scientists to look at the rest of the periodic table. If we cannot cook silicon hot enough to make it good, maybe we should use materials that like the cold. One such material is oxide semiconductors, specifically indium gallium zinc oxide, or IGZO. Originally developed for display panels, IGZO has a superpower. It can be processed at very low temperatures, even room temperature, and still function as a decent transistor. The killer feature of IGZO transistors is extremely low leakage current. When you turn them off, they stay off. This makes them perfect for DRAM cells. A 2-transistor zero-capacitor DRAM cell, built with IGZO, can hold data for vastly longer than standard silicon, potentially removing the need for constant power-hungry refreshing. IGZO is ideal for the memory layers in a 3D chip, stacked on top of high-performance silicon logic. Another material making science fiction a reality is carbon nanotubes, or CNTs. The Skywater Technology Foundry, in collaboration with MIT and DARPA, has been developing a 3D SoC platform using carbon nanotubes. CNTs can be deposited from a solution at room temperature and are naturally high-performance semiconductors. The Skywater breakthrough demonstrated a process where a bottom layer of standard silicon logic is covered with multiple layers of CNT-based logic and RRAM memory. Because the CNTs are processed cold, you can stack many layers without damaging the bottom. This is one of the few M3D technologies that has moved from lab curiosity to foundry prototype. Looking further out to 2030 and beyond, transition metal dichalcogenides, or TMDs, like molybdenum disulfide or tungsten diselenide, are the ultimate M3D materials. These materials are only a few atoms thick, known as monolayer. This allows for ultimate electrostatic control, meaning you can make the transistors incredibly short without them losing their switching ability. Many TMDs can be grown or transferred at temperatures compatible with the back end of the line. The vision is a chip with 100 layers of atomically thin TMD transistors, a superlattice of computing power. This leads us to the complementary FET, or CFET, the convergence of transistor architecture and 3D integration. In a standard CMOS chip, you need two types of transistors, N-type for electrons and P-type for holes. Usually they sit side by side. In a CFET, you stack the N-type transistor directly on top of the P-type transistor in a single monolithic pillar. This instantly cuts the footprint of a logic cell in half. IMEC predicts CFETs will become the standard device architecture around the A5 node, or 5 angstroms, in the early 2030s. This is internal monolithic 3D integration happening inside the transistor itself. However, we have the materials and the manufacturing process, but we have a major problem. We don't have the software to design these chips. Electronic design automation tools have spent 50 years assuming the world is flat. They know X and Y coordinates, but they struggle with Z. Designing a monolithic 3D chip with today's tools is like trying to design a 100-story building using software meant for 2D floor plans. Currently, researchers use a pseudo-3D workaround. They design the chip as if it were one giant 2D layer but with the cells made half as small. Then, a script folds this design, assigning half the cells to the top tier and half to the bottom. They also use Cascade 2D, treating the top and bottom tiers as two separate blocks that just happen to be very close, using anchor cells to represent the vertical MIV connections. New challenges arise, such as partitioning. How do you decide which part of the circuit goes on top? Do you put memory on top of logic, known as block level? Do you put the N transistors on top of the P transistors, known as transistor level? Or do you mix and match logic gates, known as gate level? Gate level partitioning offers the best wire length reduction, up to 50%, but is the hardest to design. Then there is the thermal trap. In a 2D chip, heat rises from the silicon and escapes through the heatsink. In a 3D chip, the bottom layer is trapped under a blanket of upper layers. The heat has nowhere to go, creating hotspots that can fry the chip. New thermal-aware floor planning algorithms are needed that know not to stack two hot components directly on top of each other. Power delivery is also hard. Delivering power to the bottom floor requires routing power cables through the penthouse. This is driving the adoption of backside power delivery networks, putting the power grid on the back of the wafer so it doesn't clutter up the signal wires in the stack. Despite these challenges, the commercial roadmap is becoming clearer. We often forget that monolithic 3D is already a mass-market reality in storage. 3D NAND flash, the memory in your phone, is a monolithic stack. Modern NAND has over 230 layers. It worked first because NAND is repetitive, utilizing the same cell copied billions of times. The future of NAND sees it scaling to 1,000 layers by 2030. The next step is logic on memory, expected between 2025 and 2027. The low-hanging fruit for logic M3D is stacking memory directly on processors. While typically classified as 3D packaging, the pitch of hybrid bonding is shrinking so fast that it is blurring the line with monolithic. Skywater's 3D SoC is the leading true M3D logic project, aiming to beat the efficiency of 7 nanometers chips using an ancient 90 nanometers node by integrating RRAM memory directly on top of CNT logic. This proves that geometry isn't everything. Topology matters more. The ultimate goal is logic on logic in the 2030s. As we move to angstrom-scale nodes, the standard cell will become a 3D structure, and by 2032, the CFET will likely be the standard transistor, making every chip a monolithic 3D chip by definition. We aren't building monolithic 3D chips just because they are cool. We are building them because modern computing has hit a bottleneck that 2D cannot solve. The first killer application is the AI revolution. Deep neural networks are hungry. They require billions of weights to be fetched from memory for every single calculation. In 2D chips, fetching this data takes 100 times more energy than doing the calculation itself. With monolithic 3D, you can put a layer of non-volatile memory directly on top of the computation logic. This is computing in memory. Data travels microns instead of millimeters, bandwidth explodes, and latency vanishes. Research shows M3D can improve the energy efficiency of DNN accelerators by 22 to 50% immediately. The second application is neuromorphic computing. The human brain is not a 2D sheet. It is a dense, 3D tangled web of neurons and synapses. To emulate the brain, hardware must be 3D. A biological neuron connects to 10,000 others. 2D chips struggle to route this many wires. M3D's vertical vias allow for massive, dense, brain-like connectivity. It allows for the integration of analog synaptic devices on top of digital neuron firing circuits, creating a physical structure that mimics the cortex. Finally, there is the everything chip. Imagine a contact lens that has a sensor to detect glucose, a processor to analyze it, a radio to transmit it, and a battery to power it. In 2D, this is too big. In M3D, you stack them. Tier 1 is high-performance logic for data processing. Tier 2 is analog RF for communication. Tier 3 is the sensor array for input. This IoT on a speck of dust is only possible with monolithic 3D integration. The path to the vertical future is not without potholes. Testing is a nightmare. How do you test the bottom layer of a chip when you have already buried it under the top layer? If the bottom layer has a defect, you have wasted the time and money building the top layer. The solution is built-in self-test circuits integrated into every tier, allowing chips to diagnose themselves as they are being built. Thermal management also needs an upgrade. A 3D chip is a dense block of heat. Researchers are exploring microfluidic cooling, etching tiny channels between the layers of the chip and pumping coolant liquid directly through the silicon stack. They are also looking at thermal vias, dedicated dummy vias made of copper or carbon nanotubes that don't carry electricity but serve solely as heat pipes to wick thermal energy away from the hot bottom layers. In conclusion, the era of free scaling is over. We can no longer just shrink transistors and expect better chips. The next 50 years of the semiconductor industry will be defined not by how small we can make things, but by how well we can stack them. Monolithic 3D integrated circuits represent the inevitable evolution of microelectronics. They solve the interconnect bottleneck, shatter the memory wall, and enable the density required for the next generation of AI. From the 1,000-layer flash memories in our pockets to the brain-inspired supercomputers of the future, the skyline of silicon is rising. We are leaving the flatlands behind. Thanks for listening to G Fun Facts Online.